Hello, this is Pete Golden here. I'm going to take you through the solutions for the multiple choice questions in the practice progression paper that you've been doing. The way I'm going to do this is I'll reveal the answers gradually, so if you think you know where I'm going with the answer and you think you can solve it, the rest of it yourself, just pause the video and see if you can carry on, and then carry on playing to see if you get the answer right. All the answers will be underneath this grey box that's on the right hand side, so as I reveal the answer you'll see the answer there. So let's have a look at question number 1. At which point A, B, C or D does the object have maximum velocity? So we've got S for displacement on the vertical against time, and everyone should know the link between displacement and velocity. Velocity is the rate of change of displacement. So in a graph of displacement against time, we've got to look for where the rate of change is greatest. So the velocity of objects at time t, that's any particular time, is equal to the gradient of the displacement time graph at time t. So those red lines that you can see there are tangents, and the gradient of each of those tangents gives you the velocity at that point. So in this case, B's got the steepest curve, slope, so the highest velocity. Okay, let's go on to number 2. An object is travelling to the right with momentum 40 kg meters per second and collides with another object travelling to the left. Now we're given the some information: initial momentum 40, final momentum 10. So another important part to this is that it's actually asking us for the change in momentum of Q, not P. So let's just go to our definition of what we mean by change in momentum. It's final momentum minus initial momentum. If we then think about what that means, that would be 10 minus 40, given the data that we're given, and that equates to minus 30 kg meters per second. So that's the change in momentum of P. What we've then got to remember is that the change in momentum of Q will have the same magnitude, but it will act in the opposite direction. That's because at the collision, the force that decelerates P is in the opposite direction to the force acting on Q. So the change in momentum, or the impulse, is in the opposite direction. Okay, so for this one, we've got answer C. Question 3. Now this is quite a good one to look at as a general case as well, because these types of questions come up quite a lot, where you're given some initial information and then a change is made in some way. In this case it's to do with the wire's length and diameter, and the question is about the impact of that change. So the question is asking us about the resistance of a wire, and we're told at the beginning that wire P has a particular length and diameter and resistance of 1 ohm. The other wire has the same metal, so therefore it will definitely have the same resistivity. It has a different length and diameter. So when we look at the first equation we'll use, R for wire P is rho L over A. We know that that's 1 ohm. Now if we then write out an equation for wire Q, we can start off by saying, well, as well as the length being 3 times, we know the diameter is twice as big, and that means the cross-sectional area will be 4 times as big, because the area is pi d squared over 4. And if you double the diameter, then squaring d will be 4 times the area. So once we've got that, we can then go to write out the equation again, this time for wire Q. It's still the same equation, rho L upon A, but this time it's rho times 3L, and because we know what's happened to the area, it's over 4 times the area. That is the same as writing, we just take out the 3 and the 4, 3/4 of rho L over A, and we already know that rho L over A is 1 ohm. So we're pretty much there now. We know that our answer is going to be 3/4 of 1 ohm, which is 0.750 ohms, and therefore this one is answer A. Okay, so let's go on to number 4. Just get rid of that box there. So two resistors of resistance 2 and 4 are connected in series across the terminal of a cell, EMF 1.4. Now this circuit is really 3 resistors in series. Although this is an internal resistance that we can't see in the circuit, it's acting just like a resistance in the external circuit. So if we want to work out the voltage across this resistor, the 2 ohm resistor, we need to know what current's flowing through it, and then we can just use Ohm's law. So we start off with Ohm's law, and then we can say, right, well, we know that the current in the circuit will be the EMF divided by the total resistance, which is 1 plus 4 plus 2. And then if we then use that same equation, but this time we're going to use it across the 2 ohm resistor, so we're going to multiply the current by the resistance. We've got an expression for the current up here, so we can now get our voltage across the 2 ohm resistor as 1.4 over 7, which is what we had up here, multiplied by 2, that gives us 2.8 divided by 7, 0.4 volts, and there the answer is A. Okay, number 5. Uncertainties. Now these are common questions, they're ones that we will get asked in most papers. How do we combine uncertainties? We're told that we want to calculate the power, and we know the current and the resistance. Therefore, we've got a calculation to do for the percentage uncertainty of both I and R. So, first of all, let's work out the percentage uncertainty in the current. It's 0.2 divided by 4, and that gives us a 5% uncertainty. We can then do the same calculation for R, and that gives us a 10% uncertainty, 0.3 divided by 3. And then the rules of combining the quantities are, if we have a squared term, we multiply the percentage by 2. So we've got 2 times 5 plus 10. And that gives us answer B. Okay, question 6. So this is really testing your understanding of key terms as much as anything. You've also got to do some calculations based on this graph. A car is driven at constant velocity until the driver sees the obstruction ahead at t equals 0. The velocity against time graph is shown as the driver brings it to a stop. The thinking distance is 10 meters. We've been given the information about how long it takes for the driver to actually apply the brakes when they see the obstruction. We know that this graph is constant velocity until this point here, and that occurs at 0.5 seconds. We also know that the area of that rectangle represents 10 meters. So we can work out what this velocity is. So, thinking distance is 10 meters, which is the highlighted section. The area therefore is V times 0.5 is 10 meters. Rearranging that for V, we get 20 meters per second. So that is 20, and that means we can now work out the area of the triangular section as well, which is the braking distance. Braking distance is the area of the triangular section, which is 20 times time of 2, from 0.5 to 2.5, halve it because it's a triangle, and we get 20 meters. So the braking is 20, the thinking is 10, and that means we then get an overall stopping distance of 30, adding those 2 points together. Okay, on to number 7. Basically, this is knowing how to calculate stress. It's force divided by cross-sectional area. So we have been given 3 kilogram mass is hanging, so we need to calculate its weight because the weight is acting on the wire. And then we need to divide that by the cross-sectional area, and I've done that as pi d squared over 4. just got the value in there already. That gives us 9.7 times 10 to the 7 Pascal, which is answer D. Number 8. Really, this is straightforward if you remember what goes on with a semiconductor. Usually there's some way of increasing the number density. In the case of the LDR, as light intensity increases, what is it that's changing? Well, in the case of an LDR, as the light intensity increases, the light energy create more free electrons. So we're ending up increasing the number density. And so the answer is C. Number 9, we've got a trolley moving in one direction and a force is applied in the opposite direction. So it's going to decelerate and then that force is removed. What is the magnitude of the final momentum? So this time we can use our equation impulse Ft equals mv minus mu. That's the change in momentum. We know how we know what force is acting for what time, and we also know what the initial momentum was because we've got the mass and the velocity. So really it's just about rearranging this to find out what mv is equal to, and then we'll have our answer. So substitute the values in. Now Ft, F is minus 3 because it's acting in the opposite direction to the way the trolley is moving, and it acts for 1.5, so that's that term there. Then mu is 1 times 2. We end up with a negative 4.5 plus 2, so overall we're going to get mv is minus 2.5. But the question up here says, what is the magnitude of the final final momentum of the trolley? So it's not the sign that we're interested in, it's the magnitude. So there's just a note there about the force, and because we're after the magnitude, it's 2.5. So that answer is B. Question 10. Now this is a topic you haven't yet done, so I'll leave this one. The photon energy though, you could get started on this if you wanted to. Photon energy is equal to the work function plus Ke max. Now that equation we will study in much more detail in quantum physics. So not essential to do it now, but here we'll be talking about particles of energy. Okay, on to question 11. In order to answer this question, you really need to know the definition of coherence. Coherence is to do with phase difference. So answer D on this one. Then question 12. We've got a standing wave. Inside this tube we have 3/4 of a wavelength, and the length of the tube is 60. The question is, what's the wavelength? So we could write out a simple equation that L is equal to 3/4 of lambda. Since we know what L is, it's 0.6, we can rearrange the equation for lambda, so we get 0.8, so the answer is D. And then for 13, for this particular question I've chosen GPE equals mgh as a way to work out the base units of energy. You could have used any equation where energy is equal to some term, some expression. So for example, K equals a half mv squared, work done is force times displacement. There are lots of energy equations throughout the course where it wouldn't matter which one you chose, you still get the same answer. So if we go through this, we get GP would be measured in joules, and then for M we've got kg, for G we've got ms to the power minus 2 acceleration, and M replace the meters for the height. And so there we get the expression which is shown in D. Okay.